Thanks very much, and thanks for the invite, Klaus, and I'm very sorry for the grief I caused you. So my theme today is to talk about false cluster correlations and exemplify this with an experimental observation that we've made in recent years. Our research group has been involved in studying conditions of the limits of stability of finite nuclei as described by an equation of state, essentially a mean field plus superposition of internal structure of the products of the reaction. And we use nuclear reactions of different kinds to study these effects. The outline of my talk is, since there are a number of people not working in the audience, not working in nuclear physics, I thought it would be good to give an introduction, a sort of illustration of how nuclear correlations are important in our science and the study of nuclear structure and reactions. Everybody knows about the success of the shell model, which is the mean field theory, but this is by no means the entire story. So I will discuss in some detail experimental results after that. Multiple neck rupture used in the reaction of a calcium-48 projectile impinging on either a neutron-poor target tin 112 or a neutron-rich target tin 124. The energy, the bombarding energy, is 45 MeV per nucleon, which may not tell you very much, but let me tell you that that's enough energy to completely disintegrate and disassemble the system of projectile and target several times over, maybe 5 times over. But essentially, that's never observed in real-life experiments. Instead, you see something like in this picture, in which is a simulation in a hybrid QMD calculation, in which you see the remnants of calcium-like and tin-like fragments emerge from the reaction, and in between a bridge that we call a neck of particles, which shows some clumpy structure. I should give credit to my collaborators, my PhD students, and a senior scientist, Jan Tücke, and also would like to thank the CESU collaboration, the LNS laboratory in Catania, Italy. Okay, so correlations, in particular cluster correlations, require some identification or definition what we understand as clusters in nuclear science and why this is an important concept. So we understand as clusters a sample of nucleons with, say, 2 to 3 protons and the same number of neutrons. So typically helium up to something like carbon, oxygen, which are either embedded as substructures in larger nuclei or emitted from such nuclei. Okay, so light nuclei and heavy nuclei, how do they differ? Give you a few examples here. This is taken from the textbook, showing the charge distributions, the radial profile of the charge distribution of a number of nuclei. And if you pay your attention first to a heavy nucleus like bismuth, you can see the constant density, charge density for a few Fermis, And this is a sort of central region at saturation nuclear matter density, which is on the surface at large distances, fading out into a diffuse surface region. Okay, so that's for a heavy nucleus. If you look at a nice light nucleus, a typical example of a cluster, you see something different. The distribution does not have a long distance, radial distance, essentially constant density, but is essentially all surface, very diffuse and essentially fluffy stuff like cotton balls or something like that. So essentially the density, the mean density of a light nucleus, light cluster, is relatively low as compared to that of a heavy nucleus, which makes a lot of difference when you think about a simple quantum mechanical correlation between the density of states and the matter density. Light clusters, because of their low matter density, mean matter densities, have the possibility to harbor a large number of states, relatively spoken, per nucleon. So one of the measures of the number of states you can get from just simple Fermi gas density of state expression, which is given here. The number of states goes with the exponential of the 2 times square root of a little a times the excitation energy of a nucleus. And this little a is essentially a scaling factor or scaling parameter that tells you how many states there are in the nucleus. And this can be fitted to experimental values. And the fit is shown here, actually divided by the number of nucleons plotted versus the number of nucleons A, so the mass number. You can see something that approaches a constant value for very large nuclei, those that have a constant saturation density in the center region, and the density of states, the number of states available to nucleons increases typically by a factor of 3 or so for the clusters we are interested in, as compared to the value associated with very heavy nuclei, the bulk value. Okay, so this means that there are a large number of states available for a reaction process whenever clusters are involved, as compared to heavier nuclei, which has an important effect on decay and reaction mechanisms. Because the connection between number of states and entropy, of course, is clear from simple quantum mechanics. So this means entropy carrying possibility for clusters is enormously larger, by a factor of 3 at least, e to the 3 larger than for heavy nuclei. Now, there are other parts of interest in cluster structure of nuclei because of their the low density of the clusters. You would not expect large clusters to be present in the ground state of heavier nuclei. But as soon as you take a nucleus such as neon and heat it up, provided with excitation energy, it will expand and also decrease in matter density, being able to, in principle, plausible, I think, to accommodate cluster structure, subcluster structure. And so, in fact, a number of nuclei are known to be quote-unquote alpha particle nuclei. And the scheme that you can see here for neon at about 4.7 MeV, there's a certain probability for the excited neon state at this energy to be composed or have a composition, a component of an oxygen nucleus with an alpha particle attached to this. At even higher energies, you can, or it has been suggested that a carbon-12 is associated with 2 alpha particles, making the main structure of this level. Now, the experimental proof of this kind of structure, internal structure of these nuclei can be made in several different ways. I show you one of them here, which is the excitation energy for neon 20 on the 12 MeV state here as a function of additional spin, which means on this state as a band head, you can produce a rotational band, and this is a quadratical scale you can obtain from the slope the moment of inertia for the rotation of the system, and this actually turns out to be as expected for an elongated structure such as this. Nuclear experimentation has turned to rare ion beam experiments in which people are trying to look at the deviation of internal nuclear structure from predicted shell model structure from mean field. And the idea is that new structures will appear and actually have been observed. One way of understanding how cluster structure can occur is from taken from a paper by Freya, showing that if you want to add more and more particles, more and more nucleons of the same kind, say more and more neutrons, one way of achieving that is for the nucleus to deform. And this is the level scheme for harmonic oscillator. This is a spherical oscillator, and as you deform it for an actually symmetric system, you can see how all these states develop, come closer to zero, so the number of states at high angular momenta increases, becomes accessible. This also means that the surface states increase in their numbers, and the entropy is such that then nucleons would accumulate on the surface of the nuclei, which with more and more added neutrons will deform and essentially will have a propensity of splitting essentially into subclusters, with the neutrons providing the chemical binding, such as electrons in atomic molecules. Now, there's another important aspect of cluster emission, which has to do with the excitation of the high excitations of nuclei. If the nucleus is excited, for example, by a fusion reaction to an excitation energy of something like from 0 to, say, 5.5 MeV per nucleon, then the most important decay mechanism is the boiling off of constituents, so boiling off of protons and neutrons. However, when the excitation energy gets higher, a new process becomes possible, namely the emission of clusters. And the effect, the reason for that, of course, is that clusters have, like nuclei, have a large entropy carrying possibility, so that at these excitation energies, it pays to emit carbon or an oxygen rather than 12 or 16 nucleons. In fact, you can make, and this is what we've done, looking at the effect in terms of a very simple semi-classical calculation in which the level density parameter, which is the measure of how many levels there are, for an increasing excitation energy, you get probability for cluster formation, which has a very steep slope up to 1 or 2 MeV per nucleon, which for a gold 197 gold isotope means that you're talking about 200 to 400 MeV of excitation energy, which is sort of the stability limit of this nucleus. At excitation energies of that kind, you can predict, and this has been observed essentially, that the probability for the emission of an oxygen cluster is of the same order as the emission of a single proton. Okay, so this is enormously interesting, and at the time was unexpected. Okay, so this is one of the effects of cluster emission, which is new and has been discovered in energetic nuclear reactions. Now, if there have been other experiments done in which highly excited systems have been produced in fusion type reactions, which produced an ensemble of several fragments and number of nucleons in a process which is called multifragmentation. This process was associated or also known as nuclear liquid gas phase transition. Now the debate is still going on, even though the activity in this region has dropped somewhat. But whether or not this process is really understood theoretically is still under debate. Okay, so these are cluster effects in nuclear reactions and nuclear decay. New emphasis of nuclear studies are associated with the cosmic or the chemical evolution of the cosmos or the universe. Nuclear astrophysics has already profited from the cluster structure idea. I just mentioned the Hoyle state in carbon-12, which is a 0+ state at 7.6 MeV, which can be understood as having a large component of 3 alpha particles. So it has a subcluster structure, which turns out to be energetically almost degenerate with an entrance channel of beryllium 8 + 1 alpha or 3 alpha. So that's either a 3-body collision between 3 alpha particles or a collision of 1 alpha particle with a short-lived beryllium 8 nucleus can find an easy access to producing a carbon-12 nucleus out of the initial reaction projectiles. Okay, so this is a well-known cluster effect in nuclear astrophysics, attributed with the main production mechanism of carbon-12 in the universe. Another application now of the cluster structure of projectile nuclei is in the case of the Trojan horse reaction or surrogate reactions in which a difficulty in transferring a particle, say X, to a target nucleus is just circumvented by transferring it by stripping off this particle if it is in the cluster structure of a projectile just in flight. As the projectile flies by the target, this cluster, if it is present, can be stripped off and captured by the target. So this is a very well-known method which is also used at the LNS in Catania. Okay, so far the illustration of why it's the concept of clusters and therefore the understanding of cluster correlations is important for nuclear structure and nuclear reactions. Now I'll come to a discussion of an actual experiment in which we observe multiple neck rupture in a reaction like this. We just heard a talk that fission is still of interest, and people are trying to understand the separation or the splitting of one nucleus into two, and as the system plutonium-240 that the speaker discussed slides down the hill, a neck, meta neck is formed between them, which eventually separates. Now this happens, this is a general phenomenon which is expected also for nuclear reactions, at least transiently, at least for some time. When a projectile approaches the target up to from a distance of something like 2 Fermis, then the surface interactions are such that they create a force-free field in between. So now there is no force, it's sort of a Lagrangian point between these two nuclei. And so now what happens? If the time is available, of course, what will happen is that nucleons from the target and the projectile are able to fill this space and produce a massive neck, so that you really have a completely filled mononucleus, which has a sort of an odd shape, but nevertheless has a neck meta bridge between projectile and target. However, time is needed for that. Now, typical velocities of nucleons inside the nuclei are of the order of 20 mega electron volts, so 20 MeV. At the surface, the velocities are much smaller than that. Now, the bombarding velocities that we are talking about are a factor of 2 or 3 higher than the velocities of the nucleons in the outer regions that are actually available for the transfer. So you can see both the difficulty and also the possibilities associated with that by changing the speed of the projectile-target interactions. You can actually allow more or less time for nucleons to fill the area in between, so that you have a control mechanism to produce necks of different consistency and different densities, perhaps. So you can control the dimensions, you can control the chemical consistency, namely the number of neutrons versus protons, and you can influence the time evolution of the neck. So in other words, you can change, in principle, the properties of the neck and study its dynamics. And this is what we have been trying to do. And the basic reason for doing that, trying to explain this busy slide. Most metals are tested for their equation of state by taking a bar and putting a load on the bar and see how it breaks. Brittle materials, brittle metals have a clean break, and as metals become more ductile, like lead compared to titanium, the bar produces a neck, and the shape becomes necked in. So this is called a neck. Eventually the neck will snap, but you won't expect that anything else but a simple neck snapping will happen. And this will be expected for a number of materials. Maybe some exceptions are mercury or so. For a nucleus, if you produce a bar, a neck of nuclear matter, you expect to be able to test a similar equation of state, which is represented here by a graph showing isotherms of pressure versus density of the material. So the various equations of state have been suggested, but essentially they have the same features. They are sort of quadratical and increase towards normal matter density, and increase to the other side for zero density, which means complete disintegration. And the equilibrium position is at this point, and this has been calculated, for example, first by George Bursch, who was also mentioned in the previous talk, as negative 0.7 MeV per cubic Fermi. So this is the so-called tensile strength of nuclear matter. As nuclear matter is excited or changed in chemical A/Z ratio, or number of neutrons versus protons, the equation of state, the curves become flatter and flatter, and you can see that the minimum, the equilibrium minimum, moves to lower densities, for example, with increasing temperatures. So what this means practically is, if you can somehow exert, need another graph, exert a pull on the bar exceeding the negative 0.7, the negative 0.7 MeV per cubic Fermi, then you can pull the piece apart and produce a necked in shape, so that eventually it will break. Depending on how you do this, the break will be more or less clean. So now a description about the neck experiments that we have made, and I already said in the title that the rupture of the neck that we observe is by no means as simple as that of a macroscopic metallic bar, but has interesting features. Now, how to identify experimentally particles that come from the neck. So if the neck actually breaks, that if it's produced in a reaction and then we manage to break it up, how do we identify the particles? Now, for that, you have to think about what competition there is. The competition for particle emission are massive projectile-like and target-like fragments in a typical reaction of the kind that we're talking about, where projectile and target still are present as main remnants in the exit channel. When these particles, when these fragments are hot, they emit particles in essentially random directions. In velocity space, this means that you have a sphere at given energy of the particle around the velocity of the emitter and the center. Now, if you measure this experimentally and plot the patterns in velocity space, for example, in versus two components in velocity, you can discern a projectile and a target emitter by semicircles. Okay, this is a projection on the plane where we measure. So for protons and tritons in this particular reaction, you get a very nice picture of superimposed semicircles, and so you know that protons and tritons essentially are emitted from accelerated projectile-like and target-like fragments whose velocities are indicated by the arrows here. However, this is different for light clusters like lithiums or carbon, which are producing blobs in the velocity space which are not spherical or ring-like patterns, but are concentrated at mid-velocity between the velocities of projectile and the target after the reaction. So this is certainly not consistent with statistical emission from highly excited massive fragments. I like this picture, these data in particular, because this was the first time that the neck particles were identified and measured in this fashion and shown to come from the neck. And the second reason is we did the experiment. So the velocity of neck clusters are expected between projectile and target velocities. Now, in order to do experiments of the kind that I'm talking about, 45 MeV per nucleon, enough energy to disintegrate the system several times over, you need efficient, very sensitive research instrumentation, which we were lucky to find at LNS Catania. This is the Chimera detector, which has something like 2,000 different detector modules, and you can imagine this is a picture of the actual cone, which is the forward region, which has a lot of detectors in order to allow very sensitive, very high resolution angular correlation measurements. So you can imagine that it takes a long time to actually do the analysis of these data. And so a number of students were involved in these reactions. So just briefly a few data points just to see that we have the possibility of determine the atomic number Z and also the mass number A of most of the particles that are emitted in such reactions. I'll come back to some details about them. In order to understand what happens in a reaction like that, it's customary to look at what's called the Wilczynski plot, in which one looks at the correlation of fast fragments, which are typically the remnants of the projectile in forward direction, and see how the intensity of the cross-section develops as a function of scattering angle or emission angle. So essentially, it's a picture of semi-classical or classical trajectory idea that the projectile, when it hits the target and comes into nuclear contact, it is pulled around and interacts with the target. There's an exchange of particles of nucleons going on between projectile and target, which is associated with a transfer of energy from the collective relative motion to internal excitation energy. And therefore, you expect a relation between the scattering angle and the loss of kinetic energy of the projectile. And this is essentially what you see in these data, which are shown as two-dimensional color-coded contour diagram coming from quasi-elastic low energy loss to very high degrees of dissipation of the initial energy. You can see here from the scale, from the energy scale, going from 2,200 MeV down to 500 MeV. So there's 2 GeV of kinetic energy of relative motion dissipated, transferred into internal excitation energy. To understand this general behavior, we've developed a model based on the basic idea of transport being associated with the exchange of nucleons between projectile and target. And this is the mean value plotted here, predicted for this system, calcium plus one of the tins. And it describes relatively well this behavior that the energy of the projectile-like fragment, the remnant of the projectile, decreases as this remnant is measured at larger and larger angles. This looked very surprising to us because the original model code was developed for very low energies in comparison, and so we were surprised that it worked that well. But it turns out that wasn't quite as good as expected, because when you show the same data, the same two-dimensional plots, but now not plotted versus for the energy, the kinetic energy of the projectile-like fragment, but its velocity versus angle, you can see that the calculations do no longer fit the general mean values. So to get this kind of an energy loss, you need less of a velocity damping. Now, how can you get that? Keeping the velocity, but losing energy. Well, if the fragment loses mass, it will also lose energy at the same velocity. And so this brought us to the idea to look for the mass distribution, or the Z distributions of the products that we actually observe at forward angles. And we see that there are several groups. The projectile-like fragment remnants and a group of so-called intermediate mass fragment clusters at lower velocities. So how are they correlated? The mass of or the charge of the projectile-like fragment remnant compared compared to the missing mass that we need in order to explain the relation between energy loss and angle and velocity, damping and angle. Can imagine that something like this happens, in which the projectile loses some of the mass and is detected at some forward angle. And now if the IMF cluster actually comes from the projectile, there should be an angular correlation between those two. And this is an obvious thing to look for. And this is what we've actually done. But first, let's look at adding the two masses and charges. Charge, in this case, atomic number of one of the fragments, for example, the projectile PLF remnant, and the other one, the cluster charge. If you add them up, you can see that the maximum intensity is exactly at a Z of 20 is the atomic number of calcium-48. But the distribution is broad, and you can see the total charge is definitely extended beyond 20, and it's broader than you would actually expect from simple calculations. You also know that these processes are associated with semi-peripheral collisions. I don't probably have time to go into this, but there are ways of telling that. But for now, let's consider that the mass, the sum of the mass of PLF remnant and IMF cluster is larger than that of the projectile. Now, it looks like the projectile picked up some mass from somewhere, well, probably from the target. Okay, so let's change the target and see if we see an effect of the target. And here you see the result. What is plotted actually is the ratio of certain isotopes, say for lithium, beryllium, boron, up to nitrogen. Different isotopes are plotted versus the number. Isotones are plotted versus the number of neutrons. And what is calculated is the ratio of the same cluster emitted from the calcium. Oh, that's a mistake here. This is the tin 124 versus the tin 112. Okay, so it's the ratio of the same cluster emitted from the heavy target and compared to divided by the yield from obtained from the light target, which means that you know, as you can see here, the ratios are larger than 1 for the more neutron-rich clusters, which means that the more neutron-rich clusters come from interaction of the same projectile with a neutron-rich target. And the opposite is true as well. And so we have a proof that the additional mass of the projectile comes from the target, and therefore there is a mixing of projectile. How many? Okay, projectile and target, which is of course the neck idea. Not go to this. Looking at the difference in or the relative velocity between projectile-like fragment and IMF compared to what is just due to Coulomb repulsion, we see that there is a large increase in relative velocity. So this is not just simple Coulomb repulsion between the two partners, the PLF remnant and the IMF, but something is increasing that velocity. The relative velocity comes from a pulling. Now, this is a three-body interaction potential, which gives an idea of what is the energetics of construction of a combination of two fragments in the exochannel and target. So the neck is reproduced by just one fragment here. I don't go into the detail, but we understand the distribution of relative mass asymmetry between the IMF and the PLF remnant. But even more, we see that there's a possibility that not only one fragment, but two fragments come from the same region of the neck structure, and this is absolutely not predicted, and I think it's probably the first measurements of its kind. If you look at different types of clusters, you can mix boron, carbon, or lithium, beryllium for the couple of two IMFs, which essentially trail the projectile-like fragment and represent the remnant of the neck. Okay, so we have a snapping of the neck in 1, 2, 3 stages. Okay, so a summary and conclusions is that we've shown that in fact in these even high energy reactions, 45 MeV per nucleon, you can produce a massive neck between projectile and target, which is existing long enough so that you can actually study the disintegration of this system, the neck. And of course, we have no detailed explanation of what happens. There's no prediction that I know of in which neck snapping occurs in more than one place. The typical theories predict one snapping which is distributed at different positions on the neck, and so the mass distributions will be affected by it. But this complex distribution has not been discussed before, I think. So there are a number of simulations that we are looking into to understand this phenomena, but sort of surprising result of our measurements is that essentially this is what we observe in collisions between two nuclei, which was observed in collisions between two rows of water droplets which produce a neck, which then disintegrates into 2 or 3 particles, which tells you something about the properties of the material that we produce, at least in this heavy ion environment at excitation, and various different chemical composition nevertheless produces a picture that's reminiscent of water droplets. Okay, so liquid drop. Okay, thanks very much for your attention.